I just plugged it in.
Thank you.
Here's the turn.
Oh, thank you.
Sure. You excited?
Kind of.
You excited? I'll let you keep practicing. See you soon.
Oh,
What?
I need to mute the YouTube, I think. Oh.
Yeah.
Yeah, that's good. Yeah. Thank you. I'll see you later.
How are you feeling?
Kind of nervous. Yeah.
Yeah. You're gonna be great though.
Oh, thank you. You kind of because I think I need more time to practice.
No, you're fine. You're fine.
I want to make my side more beautiful, but right now it's good, I think.
Yeah. You always want to make it better. You're gonna be great.
Oh, you're cutting out?
Yeah.
Cool.
What is it?
Is this yours?
But no.
Okay. I need a tube. Hello, Marianne. Oh, okay. Cool. Sure. Yeah. Okay, bye.
Sorry.
这有2个我。哦，对对对，好像，对呀，登录了，卡了。Sorry, my family. 他们不会静音，所以在家里人。对。Oh my god.
You'll need this paper.
Yeah, of course she doesn't.
We always sit over here.
It's too far away from the
Yeah.
screen.
It's true. I'll sit up.
One thing I don't like this one is like text is so small.
Yeah. Yeah. Then I felt really bad from the week I went to an even year talk. I was like, we're gonna use the projector bit.
Oh,
And then Matthew was like, well, I don't know how to work that. And then Will went before me.
right, I remember that.
I mean, Will handle, he was just like, try.
Yeah.
But I think that's really nice. Oh no.
Nathan, it seems you cannot reproduce the results.
Yeah, whatever.
What happened?
Well, they might be wrong.
I could totally be wrong. I'm probably doing it wrong, to be honest.
What can't you reproduce?
Just the science paper results.
Yeah.
Oh.
Which one? What happened?
We don't know.
Yeah, it's so funny. Got one more yellow. Yeah, me, here I am. I need another one. That's good. So everybody's like, "Oh, I'm on." She put my name on it. That's how I go.
I'm so sorry. I was trying to do that.
Just imagine when they're so happy. She'll be like, hey, look at me.
It's been longer, right? So it was like.
No, he's doing that now.
No, I know, but I'm saying like for you to get to that point.
I know.
I was like, look at me.
Between
Hang on, there's too many
the-
words. That's right. Exactly.
That's a moment.
Does that TV get brighter?
Yeah, it's actually really good, right?
It's really dark.
Thank you.
You must have.
Can you hear me, Francis?
Yep, I can hear you.
Oh, I cannot hear you. What?
Is your volume up?
Yeah.
Oh, yeah. Can you hear me?
Yep, I can hear you.
Okay, good.
Everything
Good.
is good.
Yeah.
I wonder if also like because it's tilted down.
What happened? Nothing happened.
How's it brighter? Is he changing?
I don't know.
It doesn't really.
No.
Put it down.
Put it down.
Yeah, she's talking about.
Now there's a lot there.
There is a strong reflection.
Oh, the light.
What if we just turn on the lights? There you go.
Yeah, that's good. No, it's good. It's
It's
good.
good. Leave it like
It's
this.
good. It's good. No,
There's no- there's
it's
no-
getting better. I promise it's good. Okay. Great.
Bruce, are you there?
She does have a space.
I cannot hear you, Bruce. Sorry.
Did you mute yourself?
Francis, can you hear Bruce? I cannot hear.
No, I can't hear Bruce either.
So this is not.
Is this going to YouTube at the same time?
Yes.
It's just like if you have white and black flowers. Just doing three.
Yeah. How about Hulu and Netflix as well?
Do we have people on YouTube?
Yeah.
Okay, we do have people on YouTube.
Yeah, I use the normal Windows for live on TV. Yeah.
If the people will show on YouTube. The Zoom is only for the basic community.
Yes.
I see. So you don't want to show this one, right?
Yeah. Bruce, could you say something so that I can hear you?
Bruce?
Oh, okay. Cannot hear. Anyway. Bruce, can you hear us? Interesting. Francis, you can hear me, right?
Yep.
Bruce?
Is there a phone number he can call in on?
Do we have a number of Bruce? I don't know.
For the Zoom link.
Zoom link or is my phone number?
Zoom has that built in.
Zoom, yeah.
Zoom has,
You
yeah.
should
I
be
think
able
it's
to look
doing
at-
something.
Yeah. He's
think
trying
he's doing
to.
something.
Bruce, say something. No. Maybe he can hear us? I don't know.
I don't know. Can you type something into chat, Bruce, if you can?
Yeah,
hear?
maybe I'll do this.
Just like old.
No, it seems he's not even responding.
All right, so he sent an email.
Mhm.
He
Oh,
can see the
okay.
video, but he can't hear anything. He wants to know if there's a number he can call in on.
Okay, so you can check your Zoom and the Zoom invitation somewhere, and we can find a number.
Yes.
Okay,
I will copy all the
just
sheet.
copy and paste it.
She already wanted to sit all the way
Oh,
down.
maybe he cannot see us. Maybe you have to paste down the email.
Oh,
There's nothing more fun than
First one.
letting everyone see your email.
oh, this is last.
No, no, it's not.
Where is
Who's spatial?
How been
The number I can call from this.
Okay.
Okay, just reply.
Three orders of magnitude.
That's weird.
Gives more drafts than I'm ready.
Control wheel.
Yeah, send it off.
Direct.
Just send it off.
I'm gonna show that.
Which camera?
Well, he can figure it out.
I think our goal is to overload that field so that the number is actually greater than the number they allow.
I can see a video, but don't have the audio.
Oh.
Okay, interesting. Okay, you can actually see the video, actually see the chat. So,
It's in Celsius? I mean, in the
yeah,
region of Celsius.
you can try this one.
Okay.
Oh. I think you were just like.
Shift.
You're emailing him.
Yeah, we emailed him and also put it in the chat. It seems he can read the chat. He just can't hear us somehow.
Welcome to Verizon Wireless. Your call cannot be completed as dialed. Please check the number and dial again. Announcement 4. Welcome to Verizon Wireless. Your call cannot be completed as dialed. Please check the number and dial again. Announcement 4.
Well, something on this side, right? So speak to him now, maybe he can hear you.
Is that you?
Can you hear me? Don't have the audio. Phone number.
Can he hear you guys?
Welcome to Zoom. Enter your meeting ID
Maybe
followed
the
by
phone
pound.
Is that? Did he say that he
I
can
think
hear
this
you
is
guys?
from the system.
Oh,
This is from the system.
okay.
For some reason. Yeah.
Professional audio.
I think he wants to track the input.
Enter your participant's ID followed by pound. Otherwise, just press pound to continue.
Or maybe we can
Please enter the meeting password
YouTube
followed
channel
by pound.
first. Yeah, then we can work out Zoom
Okay,
later.
sure. I'll send it.
Okay, do you know the YouTube channel link?
Yeah.
Yeah, we just sent to.
You are in the meeting now. There are 3
Well, you have a
participants
YouTube
in the
live
meeting.
there. Okay, keep calling.
Wow.
Bruce? Well, I don't know if he's he can hear us or not. Not this one.
All right.
Okay, can you hear us?
I know, this one. I think it's.
He's speaking, right? Can you hear us?
Yeah,
No.
I can.
Oh, finally.
But I don't know if you hear us or not. Can you hear us, Bruce? No,
Yeah,
it seems
okay.
not right.
I have audio and video.
Could you try the YouTube channel? We also put there, and because it's also streaming on YouTube. We put the link on the chat. And we can see if he's joining us here.
I cannot see the wheels.
Yeah, and cover.
If you come sit.
Okay, well,
I cannot see
you
the
don't know
wheels.
who is there?
How to see that? Anyone knows how to see the names of the wheels on YouTube, right? Yeah.
We don't know. All right. Sorry about this.
Sorry.
Are you saying something, Bruce?
So I had like a.
You hear us from YouTube channel?
Wow. Sorry.
I don't know if he is joining there.
Carol.
That was my first thought when I was.
Yeah, cover can do it fine. I don't know if Bruce can be there.
I'll make it twice. Yeah, maybe somewhere here. Participants. But it's only he has to type anything in the chat.
Let me see if he is here.
Edit. Yeah, I don't think there's views. Yeah, I don't think there's.
Is there any way we can just call him?
I can just call him.
Yeah.
Yeah, and after my defense, we can use a new Zoom.
Well, Francis, can you just call him and maybe let him to access from the YouTube channel? I'm not sure if he can read the chat or not.
Well,
He didn't respond.
let me try calling him. Hang on.
All right, thank you.
Yeah. So can you just call us the phone? Yeah. Well, no, but
He's not there.
Hey, Bruce. So I could just put you on speaker and so you can hear Wencheng through my. Does that work? Okay, let's do it that way.
Hi, May.
All right, let me put you on speaker. Hang on. Do you want to say something, G?
Bruce, can you hear us? You can type it. You can type in the chat if you hear us.
Did
Hello,
you
hello?
get it, Bruce?
Not clearly enough to understand it.
Okay. So that's not really working. It's not clear enough for him to understand.
It's not clear enough. Well,
Oh.
can he?
I can.
You could call him.
No. We can call him.
We can call him. Yeah.
Yeah.
Do you have enough power? Can you give us a number?
Yeah.
How this charges?
So it's 619.
Well, hold on.
They tried.
619
889
Let's do old stuff.
619 889
889
2031.
2031.
That's good too.
Hello, Bruce. Can you hear us fine?
Yeah, that's better.
Okay, so we're calling from Wencheng's cell phone. Okay, hopefully he has enough power.
Enough money.
And okay, if you can hear us fine, we can start.
Yeah. Can you see I mean, you are still in the Zoom. Can you see? If I share screen, can you see?
Yeah.
Share screen.
Yeah, if you share a screen,
Where is my profile? Why customer?
you just open it again,
Okay.
share it again.
Can you see clearly my points shared?
Bruce, can you see the slides?
Yes. very well,
Okay,
thank you.
great.
Great, great.
Okay,
Okay, let's
in
work
that
on this.
case, can you put the speaker down?
Speak.
Oh, we don't need a speaker mode.
We don't need it? Okay.
Well, he will not ask the questions right now.
All
So
right.
just put it here.
Okay.
All right. So sorry for the delay. Okay, let's get started. Thank you for coming, everyone. Good afternoon to Mr. Wencheng Shao's PhD thesis defense. And Wencheng graduated from University of Science and Technology of China in 2015 with the Bachelor of Science, and also spent 3 years there, I believe, and to get a Master of Atmosphere Science. And he joined us in 2018 and working with me on Venus science and working with Francis on Enceladus. Those are very different topics. And it seems Wencheng can handle them both well. Okay, that's amazing. And I was very fortunate working with Wencheng in the last 4 years. And he's working really hard. He's super interested in theoretical questions. And unfortunately, he recently just got an opportunity to join the Venus mission in European Space Agency. And he decided to wrap up his projects and leave us soon. And so today we are going to hear Wencheng's some of his published projects in the last 4 years. And Francis, you want to say something?
Yes. So I was a little surprised when Wencheng approached me because I knew that his background was in Venus photochemistry, but he was very interested in icy satellites. And so we had an interesting time kicking around a bunch of ideas, and eventually we settled on an idea that seemed actually worth pursuing. And I was really impressed at the speed with which Wencheng picked things up, given that this was nothing like anything he had done before. And so it was, for me, it was a really happy experience working with him. So that's all I have to say.
Thank you, Francis. So, okay, so it works like this. Wencheng is going to give a talk about like 45 minutes, and then we'll open the questions to the audience. And after the end, Wencheng is going to discuss with this committee here. All right, take away.
Okay. So sorry about the technical issues. Today we have experience. And okay, so I'm also honored to work with Qi and work with Francis on the 2 different projects. So in this talk, I will mainly talk about these 2 projects. But okay, so so starting from greeting, good afternoon, everyone, and thank you for coming to my talk. And in this talk, I will defend myself in the Venus atmospheric chemical system and the ice shell on Enceladus research. So this talk mainly consists of 2 parts. One part is about Venus, the other is about the Enceladus. So about the Venus, I will mainly lead you to the understanding of the multi-year variations and the diurnal variations of chemical species on Venus. Sure.
The YouTube does not work very well.
You mean does not have sound?
No sound, and the slides is not still on the first page.
Oh, there's some latency. That's totally fine.
No. Oh yeah, just
Just unmute.
But the unmuted will have. Yeah, unmuted will have something.
I think there's a lag.
Okay, can anyone on YouTube hear me? Please type in the chat.
I think there's a lag. Yeah, it's okay. You can just ignore it. It's just a lag.
Just a lab? Okay.
How's the audio?
Oh, okay. Got it.
Okay.
Thank you. Yeah, it's just some latency. the very low latency is also a few seconds. That's still the same. Okay, and oh yes. All right, so two parts. One part is about the Venus chemical system, and the other is about the Enceladus. So first, I will go through the multi-year variations of chemical species in the mesosphere of Venus, and also, and then I will go through the dino variations of these species. And after that, I will talk about the thermal evolution and thermal equilibrium of ice shear on Enceladus. Okay, first let's see the Venus. Venus, you can say it's the evil sister of the Earth. Venus is very similar to Earth in mass and size, but right now Venus has so different surface environment from the Earth. Its surface temperature is over 700 Kelvin. Its surface pressure is nearly 100 bar. So this makes Venus scientists wonder why Venus have evolved so differently from the Earth. So that means that studying Venus should be critical elements for us to understand the evolution of terrestrial planets. So what do we know about Venus right now? In the Venus atmosphere, we have this kind of atmospheric temperature structure here. From the surface to...
Sorry, it's not advancing on Zoom. The slides are not advancing on Zoom.
Okay, I will try it again.
Sorry.
It's okay. Is that okay?
Try advancing it and see what happens.
It seems to be loading all the time.
That did not advance.
Not advanced?
No.
That's weird. Why there are so many technical issues today? Does it advance?
The audio is good, but yeah, the screen is
still frame? Freeze. Okay. Oh my god. Okay, I will. Oh my god. I will leave the meeting and again. So.
But if you turn on.
That's weird. Frozen. So.
So on YouTube, I'm still. Yeah,
Is this good?
No. So if you present if you're like in a presenter's view, the screen is frozen.
I think what you need to do is go into presenter mode before you share your screen.
Yeah. Oh, okay.
Yeah, so stop sharing, go into presenter mode.
Present mode, where is it? Present mode. Where is it?
Full screen.
Full screen? Oh, you mean?
Yeah, just go to Zoom.
Okay.
Share
again. Share this one, I think. That's this.
Yes.
Okay. Thank you, Rachel. Oh my god. Today is an awful day. Okay. Okay. So I think there's no other problem right now. Hope so.
Close the box on the screen.
Huh? Close the. Okay. All right. All right. Okay. So what do we know about the Venus atmosphere right now? From the surface to 50 kilometers, we have troposphere. And from the 50 to 70 kilometers, we have cloud layers, which can be further separated into 3 layers: the lower, the middle, and the upper cloud. Above the clouds, until 100 kilometers, we have mesosphere. In this region, in this mesosphere, the photochemistry and the dynamics are interacted with each other complicatedly. So in my talk, I will mainly focus on the mesosphere of this Venus. Above 100 kilometers, we have thermosphere. And before we moving on, I want to introduce you something about the sulfur cycle on Venus. So sulfur dioxide will be released from the surface by volcanism and be transported to above the clouds, where it will react with oxygen to form the sulfur trioxide. Sulfur trioxide reacts with water, form sulfuric acid, and this acid condenses. Oh, sorry. Oh my God, sorry. Okay, so that's no problem.
You might have to go and present.
Yeah.
Okay. Sorry about the interruption. Okay, so sulfuric acid will condense, rain, and evaporate, and retain the sulfur element to the sulfur dioxide. Sulfur dioxide will finally reach the surface by weathering processes. All right, so right now we have observations of sulfur dioxide, which is the critical element of this sulfur cycle. So since right to the left, I show you the decadal variations of sulfur dioxide, which can be the interpretation of an indirect evidence of surface process like volcanism. To the right, I show you the spatial distributions of sulfur dioxide, which has the plume and patchy features. So this makes us wonder what processes are responsible for these temporal and spatial variations in the Venus atmosphere, specifically in the Venus mesosphere. So I want to answer this question, but I will separate it into two parts, two small parts. One part is about spatial, the temporal variation. So first, I studied the temporal variations of sulfur dioxide and water around the cloud top. The Texas IRTF, the ground-based instrument, has for the first time observed the co-evolution of sulfur dioxide and water around the cloud top, or at 64 kilometers. So to the left, you can see how the two species vary with time. If we put these these observations into a scatter plot, then we can see they are anti-correlated. So I want to ask what controls the anti-correlation of these two species. In my work, I have two hypotheses. One is the sulfur chemistry in the mesosphere. In this chemical network, sulfur dioxide and water consume each other. They may cause one higher and one lower. Another hypothesis is the vertical mixing, or you can say eddy diffusion in the cloud region. So this kind of vertical mixing transport efficiency may also affect the mixing ratios of sulfur dioxide around and water around the cloud top. So to answer my question, I used a 1D chemical model, and this model has involved 51 species, over 41 photodissociation reactions, and over 300 neutral reactions. So this model has been developed for decades, and it has been proved successful in reproducing the chemical profiles in the Venus atmosphere. I will use this model to stimulate the mesosphere of Venus, and the lower boundary is set at 58 kilometers. So I will So I will vary the lower boundary mixing ratios of sulfur dioxide and water to represent the lower atmosphere perturbations. Here I'm going to show you a plot, and this plot has the horizontal axis of water at 58 kilometers, or you can say at the lower boundary. And the vertical axis is the sulfur dioxide mixing ratio at 58 kilometers. So we have simulated multiple cases, and for these cases, if we plot the mixing ratios around the cloud top by color here, then we can get this parameter space. So in this plots, to the left, I have the sulfur dioxide dependency. The dependency of sulfur dioxide around the cloud top on the lower boundary mixing ratios. To the right, I have the water mixing ratio, and its dependency on the lower boundary mixing ratios. So from this space, we can separate it into 3 regimes. Each regime is characterized by some physical or chemical process. Here I care about regime 1 because I already plotted the observations in these plots. So that is shown by the white dots. White dots here, all of them located in the regime 1. And so what's the characteristic of this regime 1? This regime 1, you can see when sulfur dioxide is higher and the water will be lower. So it seems they have the anti-correlation. And from our exploration, this anti-correlation is caused by sulfur chemistry in the middle atmosphere. So sulfur chemistry here, as I already said, the sulfur dioxide and water consume each other when one is higher and the other is lower. So this says that the sulfur chemistry is the reason for the anti-correlation in that regime. And because we vary the lower boundary conditions, lower boundary mixing ratios here, so the lower boundary variations cause the temporal variations of this species. And this says that these temporal variations could originate from the lower atmosphere process. So what about vertical mixing, the second hypothesis? So I show you a plot that in this plot, the vertical axis is sulfur dioxide around the cloud top, and the horizontal axis is water around the cloud top. And the red crosses in this plot is from observations. Triangles are from our simulations. So when we increase the transport efficiency, and these 2 species are positively correlated. So this says that eddy diffusion alone cannot explain the anti-correlation. So that's the simple phase of my. So that's the rough work of my first work, and here I show you the takeaways of this work. So basically, we studied the anti-correlation and the temporal variations of sulfur dioxide around the cloud top, and we explained the anti-correlation by the sulfur chemistry, and explained the temporal variations with lower atmosphere perturbations. So, and vertical mixing alone, the second hypothesis does not explain our Z observations. And this may say something about the importance of chemical species above the clouds as the indirect evidence of low atmosphere process like volcanism. So I'll stop here for 1 minute and take a few questions. Let's see. Okay, sure, thank you. Sure.
I'm interested in the observations of the sulfur oxide and the water, so what's the unit of the observation in your last figure? Like what's the unit?
Unit is actually ppm. Yeah, 10 to minus 6.
I was wondering, like when you show the anti-correlation of those two, that's how could they do the observations of Venus, and also like I think it's on multiple year scale, right? Is that value like how they get that value? Is there a similarity bias, something like that? Like how do they do the observation?
Okay, so that observation is from a ground-based instruments, and which observes the Venus disk, and basically it observes the thermal emission from this Venus disk, and get the line depth for you observe this spectra and get the line depth of sulfur dioxide with respect to the carbon monoxide, which is the main component of Venus atmosphere. So then we can get the mixing ratios of this sulfur dioxide. So that's the thing. Thank you. And okay. So if no question, I will continue. And so after I studied the temporal variations, I will move on to study the spatial variations. Since the Venus is so slowly rotating, and its solar day length is about 117 Earth days, and so this may say something about the day-night difference is so significant on Venus. So specifically in this work, I will study the diurnal variations or the local time variations. So in the Venus mesosphere, we have a complicated circulation pattern. So in the Venus mesosphere, this circulation pattern may interact with the photochemistry there and affect species spatial distributions. So if we look over the North Pole, we can see how the energy and mass are transported due to this circulation. So around the cloud top, we have the westward superrotation, and above the clouds, this superrotation will transit into the subsolar antisolar circulation as altitude increases. So in the subsolar antisolar circulation, around the noon, the atmosphere ascends and will be transported to the night side. Around the midnight, the atmosphere descends and will be transported and returned back to the day side. So this kind of circulation pattern may have an effect on the chemical species local time distribution. Actually, from observations, we have seen the local time features of sulfur dioxide. So around the cloud top, we can see the sulfur dioxide distribution, local time distribution has the two peak feature. One peak is around the morning terminator, while the other is around the evening terminator. So, and this feature is also partially observed by the Venus Express mission. So right now I want to ask what controls this two peak feature in the local time distribution of sulfur dioxide? Is it from dynamics or from the chemistry? So to answer this question, I used a combination of 3D dynamic model and 2D chemical model. The 3D dynamic model will output the temperature and the wind fields, which can be used as the input for our two-dimensional chemical model. Our model will finally output the 2D distribution for chemical species in the longitude, altitude plane. But first, I want to validate whether my model is right. So I compared my model simulations with current available observations, and we find our model can well reproduce the rough feature of these local time distributions for this species. So that's good. And back to our question. So what controls the two peak feature in the local time distribution of sulfur dioxide around the cloud top? And so in our model, these two peak feature can also well reproduced, where the one peak is around the evening terminator and the other is around the morning terminator. So how do we explain these two peak features? First, I need to introduce you the concept of semi-dynatides. So this semi-dynatide is excited by the solar heating, and in the upper cloud region from 60 to 70 kilometers, there will be these semi-dynatides. These semi-dynatides will bring out. These semi-dynatides will bring out the ascending branches of ascending motions of the atmosphere, and these will have two ascending motions. And in this upper cloud region, we also have the zonal wind. So right now we can understand these two peak feature by this semi-dynatides. So one ascending motion will bring the SO2 rich atmosphere from the lower part, and this will cause one peak in the sulfur dioxide local time distribution. And because we have a so strong westward zonal wind, it will shift this peak toward the terminators. And similarly, we have the second ascending branch in the night side. So this will also produce a second peak, which will then be transported toward the morning terminator. So to conclude, the semi-dynatides is the reason for the two local peaks of sulfur dioxide in the sulfur dioxide distribution. And westward superrotation is can explain the positions of these two peaks. Then what about the sulfur dioxide in the upper mesosphere? So in the upper mesosphere, we have observed on the day side, sulfur dioxide mixing ratio is lower than that on the night side. So in our model, so this can be explained by both chemistry and circulation. So around the day side, we have sulfur dioxide photolysis, which will destroy sulfur dioxide and makes sulfur dioxide lower. On the night side, the circulation pattern will bring some sulfur dioxide rich atmosphere downward and get abundant sulfur dioxide on the night side. So this is both chemistry and dynamics contribute to the sulfur dioxide local time distribution in the upper mesosphere. Except besides the sulfur dioxide, we also studied other species, and these species may not have enough observations. Actually, we are making predictions for this species distribution, which can be tested by future Venus missions. Like the water in the upper cloud, if we get this kind of distribution, it may reflect the dynamic pattern in the upper clouds. And fortunately, we have 3 Venus missions in plan. Right now, we have Veritas, Envision, and DaVinci Plus, which will be launched in the end of this decade. So these missions will bring us more about the variations of chemical species in the Venus atmosphere, which can also indirectly tell us more about the surface process and the ancient climate of Venus. So that's the end of my second work. So basically, we want to study the sulfur dioxide local time distribution, and we found that around the cloud top, the sulfur dioxide is mainly controlled by both by the semi-dinotides and also westward superdatation. And while in the upper mesosphere, the photolysis and the circulations both affect the sulfur dioxide day-night difference. So our model can well simulate the current available observations, as well as it will make predictions for other species distributions, which can be tested by future Venus missions. Okay, so I will stop here for 1 minute and take a few questions.
So you said the ascending motions in the dinotype is going to be responsible for the variation you have for sulfur dioxide.
Yeah.
But if you look into the curve, if you look into the curve that for the first ascending motion that you have a local minimum, but for the second ascending motion for observation, it seems like you have an increase instead of like just a local minimum. Like, do you know how to explain these discrepancies? Like what happened there that make them different?
So I may not be clear when I explain this. So the ascending motions will bring sulfur dioxide rich atmosphere to this level. And this will cause a peak instead of a minimum there. So originally, if we do not have a westward zonal wind, we will have a peak around the node. And after that, because we have also the westward zonal wind, it will shift this peak toward the terminators. So that's how it works in our model.
But for second one, you have a local maximum.
Oh, you mean the observations?
Yeah, observation.
Okay, so yeah, that is something we cannot explain right now. So it may involve the small scale dynamics like waves, but our model has a very low resolution, so we still cannot explain that stuff. So
it is a small feature or transient feature is not going to be affected. It's not going to affect the long-term observation.
I'm not
like
sure.
Averaging a lot, very long.
Yeah, that's a good question. I'm not sure. Yeah. Okay, and thank you. And
no question on YouTube.
Okay, that's that. All right, so it seems that I can finish my all right. Sorry. Okay, it seems that I can finish my talk earlier. So after that, let's see the ice shear on Enceladus. So Enceladus is the satellite of the planet Saturn, and it's an icy satellite. It's so cold, but the interesting thing is that it's so active right now. Since the Cassini flyby, we have identified the water plumes on the south polar terrain on Enceladus. Combine the observations from Cassini, we right now know that Enceladus could possibly possess a global subsurface ocean. In this ocean, the life may emerge. So this is also important for the study of astrobiology. So if Enceladus has a subsurface ocean, this makes us wonder the energy balance, the energy budget of Enceladus. So Enceladus has 3 layers, ice shell, and below it we have the subsurface ocean, and which lay down the silicate core. And so if Enceladus, from current observations, we have known that Enceladus is losing heat at a high rate by the plumes in the south polar terrain and also by conduction. So this says that if Enceladus is in thermal steady state, large heat generation must occur inside the satellite. So right now, tidal dissipation is a good candidate, but from previous estimation, this tidal dissipation seems not enough to match the heat generation, to match the heat loss of the ice shear. So, but since the Cassini flyby, we haven't studied the forced libration heating. So my question is, can the forced libration heating produce enough? Can the forced libration produce enough heat to match the observed heat loss? So first, so to answer this question, I still want to introduce what the libration is. Libration in this work can be separated into two types. The first type is the optical libration, which is caused by the eccentric orbits of Enceladus. Suppose you stand on the Enceladus and watch the primary, the Saturn, and the Saturn will induce a bulge on the surface. Since the Enceladus has an eccentric orbit, this so the bulge will induced by the since Enceladus has an eccentric orbit. If you stand on the Enceladus, the Saturn will move around, and then the tidal bulge will also move around. So this is called the optical librations. Another libration we consider about is the forced libration. This is caused by the torque from the primary. So because of this torque from primary, Enceladus itself is not constantly rotating. So its rotation rate also changes with time. Because its rotation rate also changes, if you stand on the surface of Enceladus, you also move around with respect to the tidal bulge. So this will also give you some libration, and which is called the forced libration. So if the forced libration will enhance the total libration amplitude, it will increase the heat generation in the ice shear. So to calculate the amplitude of this forced libration, we used a model by Wencheng in 2013, which will consider the finite elasticity of ice shear. Our model also considers the depth dependent viscosity in the ice shear, and the shear thickness, since it's not well constrained, is ranging from 5 to 50 kilometers. Our tidal dissipation is calculated from a simple formula in Wisdom's paper. So what does our calculations tell us? In this plot, I show you how tidal heating in the ice shear is dependent on the shear thickness. So the blue region is the shear thickness range inferred from libration data. Solid line is the total heating with the forced libration included, while the dashed line is not. So we can see when the ice shear is very thin, this forced libration will enhance the tidal heating in the ice shear significantly. However, if we plot the conductive cooling rates in this plot, the cooling rate is still much larger than the heating rate in the ice shear. So this says that is either Enceladus is in equilibrium, it's not in equilibrium, or there are large heat sources occurring beneath the ice shear. So our results tell us the fossil liberation, even though it is even though it enhances the tidal heating in the ice shear by a lot, we still cannot match the current heat loss observed by Cassini flyby. Then we wonder how the fossil liberation affects the thermal evolution of ice shear on Enceladus. So a previous work proposed that there may be a thermal runaway in the history of Enceladus, and this in this thermal runaway, if we perturbate the shear heating by a little, and this more heat will melt the shear, and the shear will become thinner. Thin shear will produce more heat and will make this scenario the runaway. So my question is that could this thermal runaway produced by fossil liberation? But first, I will do this in this methodology. I will in this plot, vertical axis is heating or cooling rate. Horizontal axis is the ice shear thickness. So here I show you two lines which represent the cooling and heating rates. So if they are configured, in this situation, the cross point of these two lines will be a stable equilibrium. Suppose we increase by ice shear by a little, and this increased ice shear will make the heating larger than the cooling rate. So this says that the shear will melt again and return to this original cross point. So that's why it is called a stable equilibrium. If you are in the opposite situation, then this equilibrium point will be unstable, which may cause the thermal runaway. So what our model tells about this equilibrium status? In our model, since the Enceladus in the history could have a high eccentricity, so we also explored the heating rate with different eccentricity here. So the blue lines in this plot tells us the cooling rate dependency on the ice shear thickness, while the other lines represent the tidal heating, the total tidal heating with different eccentricities. So we can see that the cooling rate and the heating rate can cross each other by 2 points. One is unstable, but this unstable point has two extreme parameters. That is the very thin ice shear and the high eccentricity. So we do not prefer this unstable point to happen in the recent history of Enceladus. Another point has good parameters, and it is a stable point which resists small perturbations. So we think this point, this stable equilibrium, is likely to happen in the recent history of Enceladus. However, we still know very less about Enceladus. So we need Enceladus missions like orbital lander to get more information about the interior structure and also the energy balance of these satellites. This will make us more well understand the evolution of icy satellites. To wrap up, in this work, I studied whether fossil liberation can explain the high heat loss observed by Cassini. So our results shows that even though the fossilization enhanced heat when the ice shell is very thin, this enhanced heating still cannot explain the observed heat loss. This indicates that either Enceladus is not in equilibrium, that is, the ocean is freezing with time, or there exists large heat generation in the core or in the ocean. Our results also studied we also studied the thermal evolution of ice shell and how fossilization affects this evolution. And our results implies that Enceladus is likely to be in stable equilibrium, and thermal runaway or episodic heating is unlikely to originate from the fossilizations of ice shell. So I will continue on and finish the final few slides. So after these 4 years, I have become a totally planetary scientist, and I'm honored to work with Xizhang and Francis Nemo about 2 different projects, which broaden my view. Especially when I just came here, I studied from atmospheric science major, and right now I think I'm successful in both atmospheric science and planetary science. So, and also I want to especially thank Carl, which who is right now a postdoc. And when I just came here, I studied the Venus work, and I received a lot of help from him. And I can even say without him, I cannot finish my Venus project. Okay, so due to time limits, I cannot say thanks to everyone. And so I will stop here. But I want to talk about 2 things. I think Xinting is in my YouTube live. So I will answer the question a few years ago. Xinting asked me, so what does my middle name means? So that's basically my mother's family name. It's so easy. And also the final thing is that I want to wrap out this talk by a poem. So this poem, I like it. I knew this poem in the movie Dead Poets Society. I want to cite this poem and give it to my advisors. Okay, so, oh captain, my captain, our fearful trip is done. The ship has weathered every rock. The prize we thought is won. The port is near, the bells are here, the people all exulting. While follow eyes the steady kill, the vessel grim and daring. But oh hearts, 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 oh the bleeding drops of red, where on the deck my captain lies, falling cold and dead. Of course, there are 2 other parts. I will stop here. I will not ask that. It's just to express my gratitude to all of my thesis community and my advisor. So thank you. That's all of my talk, and I'm taking any questions.
All right, any questions to Wencheng?
Is there any on YouTube?
On the audience?
Very personal and maybe silly question. You never told me your middle name. What's your middle name?
My middle name is Du. It's my mother's family name.
Okay.
Yeah.
All right, Kobe.
For your first project, could you do or could somebody do like a high time resolution observation and to see if there's like a delay between VSO2 rise and the water falling.
Hmm,
So that might be one way to test this.
that's right. Yeah.
What's the timescale of VSO2 to SO3 conversion?
I think it's or no, I think so. It's basically 1 day. So it's a chemical item. It's so lower. I'm not sure whether it will work. Yeah, maybe it will work because transparent time scale is that in the upper cloud region is a few days. I think I forgot anyway. So in that upper cloud region, the chemical time scale of sulfur dioxide is you can say in the same order of magnitude of the transport time scale. So in that region, it's so complicated. I think both staff are working together. So I'm not sure whether observations can observe this, but that's a good point. I agree with that. Yeah. No question, I think. Anyway, yeah, no question. All right, maybe I. Oh, sure.
Yeah, so for the second project,
Mhm.
what else information do you need to make your simulation better consistent with the observation?
You mean Venus?
Like, yeah, from the observations.
You mean the local time distribution of
Yeah.
sulfur dioxide? What else information do I need?
So they talk about the missions. Right? So what
Oh,
kind of,
okay,
like,
yeah.
observation?
Okay, so right now, we do not know well about the circulation pattern. Even I show you the circulation pattern in the mesosphere. In fact, it's not well constrained. Right now, we only know in the upper cloud we have a super rotation, and in the thermosphere we have a subsolar and solar circulation. But the transit region between, you can say between 80 and 100 kilometers, in this region, how the westward wind transits to the subsolar and solar circulation is still unknown. It's not well constrained. Think first, if we can, we want the wind structure in the mesosphere to well constrain our dynamic model. And then we need more observations of other chemical species like HCl, sulfur monoxide, to constrain the local time variations of other species, so that we can also understand the competitive interaction between the dynamics and chemistry. So that's the things I want, but that's only for the mesosphere. Of course, we needed to know the lower atmosphere. Right now, my model is only mesosphere, so there is the artificial low boundary. So I need more information from the lower atmosphere to constrain the transport flux of this species to the upper world. So that's the thing. Sure.
Thank you for the great talk. It's good that you are in this slide because my question is about this slide.
Okay.
I have very little background knowledge, and it's nice to see that you found split stable Bitcoin that the shell is stable under perturbations. The thickness of the shell is stable under the perturbation. I think from the plot you have showed that where the shell is, like the thickness of the shell is. So that seems to make a prediction of how thick the shell is. Is there a experimental data that can compare and to figure out, or if this fixed point is just a more qualitative
Sure, thank you. That's a good question. So right now, when I said the ICL thickness is not very constrained, I really mean that. I mean that. So, but from Cassini's limited observation, so we actually get a sense of how the thickness is. It's basically around 20 kilometers, maybe 10 to 30 kilometers. The average thickness, not the thickness variations over space, not that. Just the average thickness. So, in fact, in my plot, this stable point does not mean that I can derive the shell thickness is around 20 kilometers. is that I add a constant heat source from below the ICR. So this heat source will largely determine where this point is. So in this talk, in this slide, I only studied how the force vibration affect the thermal evolution. I do not study where the equilibrium is. So, but from current observations, we right know the average thickness is about that. As I already showed in the previous slides, this blue region is the shear thickness inferred from libration data. So that's the logical there. So actually in that slide, we do not say anything. We do not infer anything about shear thickness. So that's it. Sure.
I think you said that you were open to using other tidal heating models. Is that something that you'll do in the future?
Should I say truth? I mean, in this quarter, originally in this quarter and last quarter, Thesis and I are thinking about using this to study the Uranus satellites because it seems so interesting. It seems I'm so busy. I was so busy in this quarter and last quarter, and we did not move on in this project. So that's a pity. But I think my model is there. And if someone want to continue, so if in the future I want to continue, so I can do that also. Sorry about that, Francis.
Okay.
So maybe a weird question, but if you got to the unstable state, could you run away in like two directions and have the southern hemisphere go to the thin state and the northern hemisphere go to the thick state? Is that
this 1D model? So it's only says average thickness.
Sure.
So if we want to apply to the South Pole, I'm not sure whether it can, because usually we think the South Pole has a very thin icy shear, right? Mm-hmm. So it's about 5 kilometers, around 5 kilometers. Your light, you know, there is also free libration. The resonance frequency is very close to the dynamo frequency, so our model may not be applicable. So that's it. All right, I think that's enough. Thank you for the wonderful question. Yeah.
All right, we will just conclude the talk.
Yeah. We can talk with Barista how we work in this way.
Bruce, are you still there?
Yes, I am.
All right, we will let Wencheng to have a short break, and then we can start discussion. How about that? Thank you.
Should we use a different Zoom since you cannot enter my Zoom room?
Well, it may be a computer audio problem.
Computer audio? Okay. Oh.
Thank you, guys.
Okay. Yeah, we can still stay in this room. That's okay. Arrow, turn it. My. Next. That's all. Yeah.
So,
stop the live.
Bruce is going to join the Zoom or
and the stream. And, right.